So again, a point estimate is just a single number or just a value. For the interval estimation, in this case, you have more information than using a point estimate. So confidence interval provides additional information about the spread of the variability of the estimate. As I mentioned before, there are two parameters of interest in this chapter. The first one is the population mean mu. In this case, we can estimate the population mean mu by using the sample mean x bar. The other parameter is the proportion. The population proportion is pi, and the point estimate is p. So p is a point estimate of the population proportion pi. So again, this chapter talks about confidence interval estimation, and as we mentioned, that there are two types of estimation. One is called point estimation, and for example, the average or the mean of age is 18 years, so 18 is the point estimate. On the other hand, the other type of the confidence is the confidence interval estimation. So rather saying that the average is 18 years, you could say that we are 95% sure that the average of student ages range between 17 up to 19 years. And again, the confidence interval gives more information about the variability of the data. And again, there are two types of parameters we are interested in. One is called the population mean, and the point estimate is the sample mean. The other parameter is the population proportion pi, and the point estimate is p. So again, an interval estimate provides more information about a population characteristic than does a point estimate. Because if you go back a little bit to the previous example, here we calculated the sample mean to be just 1 point. So the average of your ages is 18 years. But the other one, I am sure that for 95% that your ages range between, for example, 17 and 19. So in this case, we have more information. Such interval estimates are called confidence intervals. And we are going to use this notation, CI. CI stands for confidence interval estimation. An interval gives a range of values, because here we have a range from, for example, 17 up to 19. In this case, this interval takes into consideration variation in sample statistics from sample to sample. For example, suppose we have a huge population, and from that huge population we select many samples of the same size. Maybe the first sample, for example, of size 50, gives average of 17. Maybe another sample of the same size might give different sample mean, 18 and so on. Suppose we select 100 samples. So here we have different sample means. For sure we should have different confidence intervals. Maybe the first one starts from 16 to 18, the other one maybe 15 to 17 and so on. So the confidence interval takes into consideration variation in sample statistics from sample to sample. But the confidence interval we have to construct based on observations just from one sample. I mean, you don't need to select too many random samples in order to construct the confidence interval. Just select one sample, one random sample, and from that sample we can construct a confidence interval. So my confidence interval can be constructed by using only one sample. From that sample we can compute the average. Now this interval gives information about closeness to unknown population parameters. For example, when we are saying weights range between, for example, 60 kilogram up to 80, and you are sure about 90%. So that means the average weight range between 60 to 80. That means the true parameter mu is close to these values. So it's between 60 to 80. Now suppose in this case I am interested in 95%. Now suppose someone else interested in 99% confidence. So do you think the confidence interval for more confident to be wider or narrower? As the confidence gets larger or bigger, the interval gets wider. So maybe from 55 up to 85. Another example, suppose we are interested in the age of students. 80% confident that your age is between, or your weights, let's talk about weights, between 70 up to 75 kilograms. 80%. 90% could be 60 to 80 kilograms, or 65 to 75 kilograms, to 80 kilograms. 95%, for example, 60 to 85. 99% from 58 up to 90. Which one is best? Which is the best confidence interval among all of these? To say that we are 80% at 70 to 75, 65 to 80, 60 to 85, 85 to 90. Which one is better? Now, when we are saying from 70 to 75, it means the interval width is smaller, or maybe the smallest among the others. So this one is the best confidence interval, because the error here is just 5. Now, here you can expect your weight, but for the other scenarios here, it's very hard to. Now, suppose I am saying that your score in statistics is between 40 up to 100. It's too large confidence interval. Suppose I am saying that I am sure with 99.7% that your score in statistics lies between 50 to 100. And my question is, can you expect your score? It's very difficult because the range is too long, from 50 up to 100. Because here I am maybe 99.7%, so I'm almost sure that your score is between 50 and 100. But suppose someone else says that I'm 95% that your score ranges between 6 to 90. It's still large, but it's better than the previous one. One else says I am 90% sure that your score lies between 70 to 85. Another one might be saying 85% that your score starts from 74 up to 80. Now here the range is small, so I can predict my scores just between 74 to 80. So we like to have confidence interval to be small as much as possible. Okay. So that's for the range. So in this case, the true parameter is very close to one of these values. Always the confidence interval is stated in terms of level of confidence. The common ones are either 90%, 95, or 99%. So these are the common level of confidence. Next slide, inshallah, will turn on the other side. Now, for example, serial example, suppose we know that the population minimum is given to be 368 and sigma is 15. Suppose we know the population mean and the population standard deviation. In reality, if these two parameters are unknown, we don't need to select a random sample, because we are selecting the samples in order to estimate these unknown parameters. But this example just for illustration. So again, mu in reality is not given, is unknown, as well as the standard deviation. But suppose from previous studies we know that the population mean is given by 360 and the standard deviation for the population is about 15. Suppose we know this information from the history or from the previous studies. Now suppose we take a random sample of size 25 and this sample gives the following information. So here we have mean of at least 68, sigma of 15. And let's see how can we construct the confidence interval as we mentioned in the previous lectures. If you remember this score, the x bar minus mu divided by sigma over root n. In this case, let's see how can we compute x bar from this equation. So z equal x bar minus mu divided by sigma over root n, just cross multiplication, you will get x bar to be mu plus z sigma over root n. So this is the value of x bar. Mu plus z sigma over root n, just cross multiplication. Now the value of z could be positive or negative. It depends on the direction of the z score you have. So if z score lies in the left side, this one is negative, the other one is positive. Because here we are talking about confidence interval, ranges from smallest value to the largest one. So z score is negative. So x bar plus equals mu plus or minus z sigma over root. Now let's imagine that the population mean is 368 and sigma is 15, and we select a random sample of 25. Let's see the range or the values of x bar might be taken. So x bar equals 368 plus or minus. Now for 95%, the corresponding z value is 1.96, if you remember that. And the other one is negative or plus, it depends on the direction of the z score. So plus or minus 1.96. This value can be computed or found by using the normal table. Times sigma 15 divided by root 25. Just simple calculation will give 362, 373.88. Now, this interval, which ranges from 362 up to 373, contains 95% of the sample means. Suppose we have 100 sample means with different values. You can say that 95% out of these 100 will contain the sample mean. That if mu is given. But again, in real life, you don't know the value of mu. So when you don't know mu, you can use x bar to estimate mu. Now suppose, on the other hand, here mu is unknown, and we estimate mu by X bar, the sample mean, and suppose the sample size 25 gives sample mean of 362.3. So this sample mean by using a sample size of 25. Now let's see how can we construct the confidence interval in this case. Now X bar is given, so my interval should be mu equal X bar plus or minus Z sigma over root n. Just replace this mu by X bar. You will get. So again, sample of size 25 gives sample mean of 362.12 plus or minus 196 sigma divided by root 25. This interval could be mu ranges between these two values, 356 approximately 0.42 up to 368.18. Now look at this interval. We know the true mean equal 368. We got this interval for X bar. Now, if mu is not given, is unknown, based on the sample we have of size 25, we got X bar to be 362, and we got the interval for mu lies between 356 up to 368. So in this case, you can say that I am 95% sure that this interval captures or contains the population mean. But you don't know exactly if this interval contains or not contain the population mean mu, because mu is unknown. So the first scenario here, if mu is given is unknown, you can say that 95% of the samples we have contain the sample means that lie between these two values. But in reality, as I mentioned before, mu is not given, so we can take a random sample, and from that sample we can compute X bar. Then we can figure out that mu ranges between these two values. But here, you cannot say that this interval contains mu 100%. But you can say that 95% of random samples like this one will contain mu with 95%. So that's the logic for the confidence interval. But again, if we select many samples, we will get different sample means. For sure. Now, suppose I have 1,000 students. I select, for example, 50 samples, each one of size 30. Maybe the first sample will give average of this value, 362. And I will end with this confidence limits. Lower limit 356, upper limit 368. I know that from previous studies that the population mean is 368. Now just ask this question. Does this interval contain mu? The range from 356 up to 368.18 covers mu. So in this case, this interval contains mu. Maybe someone select another sample of the same size, and that sample gives sample mean of 369.5. By using this equation, you can figure out lower limits and upper limits. Now again, ask yourself this question. Does this interval contain mu? The answer is yes, because 368 lies between these two values. So the first one contains mu, the second one contains mu. Look at the third sample. Suppose from my sample I got sample mean to be 360. So lower and upper limits are 354 and upper limit 365.88. Now, this value, 368, is outside of this interval. So maybe your interval will contain mu or will not contain mu, but you don't know actually the value of mu. So in this case, you cannot say my interval will contain mu. But here, if we know mu, you can say that this interval contains mu or the other one does not contain mu. But in real world, you don't know the value of mu, so mu is unknown. But you can say that I am 95% sure that this interval will continue. Make sense?
Based on the X-bar.
Based on the summary. And the other information we have, sigma and n. Again, in practice, you only take one sample of size n, so you don't need to take many samples, just take one sample. In practice, you don't know mu, so you don't know if the interval actually contains mu. However, you do know that 95% of the intervals formed in this manner will contain mu. So again, any interval can be constructed in this chapter, one of these. You cannot say that this interval contains mu. You have to say that 95% of the intervals formed in this way will capture the population parameter mu. Okay. Another one, thus based on one sample, you actually selected, you can be 95% confident your interval will contain mu. So again, this interval might be or might not covers mu. Since I don't know the value of mu, I cannot say that this interval will contain mu. But you can say that 95% of the intervals constructed in this way will contain mu. That's the interpretation of the confidence interval.
You cannot say in 19 or 99?
99, 95, whatever is. Now, the process of the estimation is, we have a huge population, and suppose we are interested in the population mean mu, and mu is not given or is unknown. We may select a random sample from this population with any size. From this sample, we can compute the average or the mean. Then after that, we can construct the confidence interval. For example, maybe I'm saying that I am 95% confident that mu is between 40 and 60. So the process of estimation, select a random sample from your population. This sample should be representative in order to generalize your results. Otherwise, you cannot do that. So this sample should be representative. And in chapter 7, we discussed 4 types of probability sampling techniques: simple random sample, systematic, cluster, and stratified. So by using this sample, we can compute, for example, the sample mean. Then after that, I will show how can we do or construct or build the confidence interval. So this is the estimation process. Now, the general formula for all confidence interval is, the general formula has mainly 3 components: point estimate, a plus or minus critical value times standard error. Let's see the definition for each component. The first one, point estimate, is the sample statistic estimating the population parameter of interest. For example, if you go back to the previous age example, and suppose x bar is 18, so you can say that the point estimate, since 18 is the sample mean, and we are interested in the population mean, so 18 is a point estimate for mu. This is the first one. This is the first component. So a point estimate is the sample statistic. X bar is sample statistic. Estimating the population parameter of interest. I am interested, suppose, in the population mean. So we have estimate. Plus or minus. The critical value. The critical value here is a table value. That means we have to go back to the normal table again. The one we had discussed in chapter 6. The critical value is a table value based on the sampling distribution in chapter 7 of the point estimate and the desired confidence interval. For example, let's talk about again 90%. Confidence. So in this case, this area represents 90%. The area from lower limit to upper limit, this area. Now again, by symmetric distribution, we know that the remaining 10% is split into two halves, 5% to the right and 5% to the left. Now the critical value in this case is the z-score. Now by using the normal table, the standardized normal table, you can figure out z in this case is negative. Look at the table. Look at 5%. Or look actually at the other one, 95%. The value is minus 1.645. The other one is 1.645. So that's the critical value, so plus or minus a critical value. Again, the table, if you are looking at 0.05, you will get this value, minus 1.6 under 4. Under 5, here we have 0.045, 0.055. You have the tip. Again, look at the end of this one. So 0.505. So again, minus 1.6 under 4. 0.505. So your answer could be either one of these, negative 1 point. So in this case, your z-score minus 1.64 or minus 1.65, or the average of these two values minus 1.645. It's better to use this one. So for 90%, 5% to the right, 5% to the left, just use the normal table, you will get these two values. So this is the critical value. Time, the standard error, it means the standard deviation of the point estimate. So the general formula for all confidence intervals is given by this equation. Point estimate plus or minus critical value times standard error. For example, point estimate is x bar, a critical value is z score, times the standard error of the point estimate. So times this SE is the standard error of the estimate. So these are the three components in order to build any confidence interval. Another definition here, the confidence level. The confidence level that the interval will contain the unknown population parameter. For example, we can say 90%, 95%, 99%. You never say 100%. So usually the confidence level is a percentage that is less than 100%. Now, for example, suppose the confidence level is 95. This 95 can be written as 1 minus alpha. 1 minus alpha equals 95%. That means the confidence here is 95%. So the error or alpha is 5%. So if the confidence level is 90%, it means the error is 10%. It is 90. So alpha is 10% and so on. So a relative frequency interpretation in this case, you can say that 95% of all the confidence interval that can be constructed will contain the unknown true parameter. A specific interval either will contain or will not contain the true parameter as we mentioned. So if you have confidence interval with confidence level 95%, this interval might be or might not contain the true parameter. So you are not sure 100% that the true parameter will contain in the confidence interval. So for this chapter we are going to talk about confidence intervals for population mean and population proportion. For population mean we will have two cases when sigma is known and sigma is unknown. Now let's start with the confidence interval for mu when sigma is given. But again, if mu is unknown, here we are talking about confidence interval for mu. Since we are talking about estimating mu, that means mu is unknown. Now the first case here we are talking about sigma is unknown, is known. But we know that from chapter 3 that sigma is square root sum x minus mu squared divided by capital N. So in order to compute sigma, we have to know mu first. Otherwise you cannot compute sigma. So how can you say that mu is unknown and sigma is given or is known?
Mu must be unknown.
So mu should be unknown. Or sigma is unknown. So sigma is known has big question mark. Because if sigma is known, that means mu should be known. If mu is known, you don't need to select a random sample to estimate mu. Make sense? I know the value of mu. So what's the goal of selecting a random sample in order to estimate mu? You are saying sigma is given. That means mu is given or mu is known. So what's the benefit of selecting a random sample in order to estimate something is known? always we estimate unknown parameter. But here, the reason why we are talking about sigma is given sometimes from previous studies. Sigma could be given, but we don't know the exact value of mu. So we are interested to estimate the population mean mu. So it might be mu is unknown, but from previous studies or from the history we have, maybe we know the value of sigma. But in real life, most likely sigma is unknown. That will be discussed next time, inshallah. So here we'll discuss just the confidence interval for mu when sigma is known. But again, if sigma is known, mu should be known. Otherwise, we cannot compute sigma. But here, when we are talking about sigma is known, it means we know from previous studies that sigma is given. Any question? Okay. So the assumptions for the first case are, mainly there are two assumptions. Number one, population standard deviation sigma is known. So we know the value of sigma. The second assumption, the population is normally distributed, but if the population is not normal, you can use large sample. In this case, you can apply the central limit theorem. Then we can say that the sampling distribution of x bar is approximately normally distributed with mean mu and standard deviation sigma over root n. So there are two assumptions here. One, sigma is known, because here we are talking about sigma is known. The other one, the population is normally distributed or n is large if the population is not normal. In this case, the confidence interval estimate is given by this equation. X bar, as we mentioned before, any confidence interval can be built by using three components. Point estimate X bar, critical value Z, forget about alpha over 2 for a minute, multiplied by the standard error of the estimate. And we know that the standard error of X bar is sigma over root n. Now Z alpha over 2 comes from the fact that we have, for example, here 95%, this is 1 minus alpha. 1 minus alpha is 95%. So 5% remaining to both sides. Upper tail will have, for example, 2.5, and lower tail the same percent, 2.5%. Now, since 1 minus alpha equal 95%, that means alpha is 5% for both sides. So this one alpha over 2, the other one is alpha over 2. So this is your Z. So Z alpha over 2. The other side plus Z alpha over 2. So X bar is the point estimate. Z alpha over 2 is the normal distribution, the critical value for the probability of alpha over 2 in each tail. And sigma over root n is the standard error. So again, this is the first formula we have in this chapter to construct the confidence interval with 1 minus alpha confidence level. So 1 minus alpha percent confidence interval for mu is X bar plus or minus Z alpha over 2 times plus or minus sigma X bar plus or minus Z alpha over 2 times sigma over square root of n. So this is a formula can be used in order to construct confidence interval for the population mean mu. The lower limit is given by X bar minus this amount. So the lower limit X bar minus, and the upper limit is X bar plus upper limit. Now the point estimate is X bar. For the lower limit, we subtract this amount from X bar For the upper limit, we add the same amount. So subtracting a specific amount and adding the same amount. This amount later we'll call it margin of error. That will be maybe week after next week. Inshallah. So Z alpha over 2 sigma over root n is the margin of error or the error because we add or subtract the same value of x1. Now this slide just explains how can we compute Z alpha over 2, and we did that for 90%. Now here for 95% confidence level, so alpha is 5%. So Z alpha over 2 in the lower tail is 1.96 minus, the other one plus 1.96. So the lower confidence limit minus or negative, upper confidence limit is plus. So the same values but different signs. So I think we talk about how can we find the critical value Z alpha over 2. This table summarizes the commonly used confidence levels, and most likely we are using 90%, 95%, 99%. So for 90% is 1.645, as we did. 95% 1.96, better to remember these values. For 99, it's 2.58. Now let's see. As the confidence level increases, now here the confidence level, as the confidence level increases, look at the corresponding Z value is also increased. So in this case, the interval becomes wider or narrower? Wider. Because here we subtract this value, this amount. Z alpha over 2 will increase. This is Z alpha over 2. As C level, as confidence level increases, Z value increase also. So that means this amount will go up, will increase also. That means the confidence interval becomes wider. So as C level or confidence level goes up, increases, the corresponding interval, the interval becomes wider. So as C level increases, the confidence becomes wider. Vice versa, if the C level decreases, narrower, the confidence interval becomes narrower. It's better to have narrower confidence interval. So again, it is better if you remember these values for the confidence level and the corresponding Z value. So that's the C level for different sizes. This slide shows that some confidence intervals may be contain mu. So the blue ones, this is the value of mu. The blue ones contains mu. The red one does not, because the mu in this case lies outside the confidence interval. So maybe the confidence interval you have to construct, it might be covers the mu or not. I have to mention just one point here. It's better to say that my confidence interval covers the mu, so you can say that I am 95% confident that the confidence interval contains mu contains the true parameter mu, rather than saying mu lies in the confidence interval. Because mu is unknown. You cannot say mu lies in the confidence, but we can say that 95% we are sure that my interval contains mu. So don't say mu lies in this interval. So it's better to say that we are 95% sure that my interval covers, contains mu. Let's do one example. Here we have a sample of 11 circuits from a large normal population. So now we have a random sample of 11. This sample is selected from normal population. So the first assumption is okay. So normality is assumed to be satisfied. Now this sample has a mean resistance of 2.2 ohms. So again, a sample of 11 circuits from a large normal population has a mean resistance of 2.2 ohms. That means X bar is 2.2. Ohms is the resistance unit. We know that from past testing, it means from previous studies, we know that from past testing that the population standard deviation is 0.35. So sigma is 0.35. So sigma is known. So the second assumption is okay. But again, as we mentioned, sigma in reality is not known. But here from past testing, I mean from previous knowledge, we know that sigma is 0.35. Now the question is determine 95%, so C level or confidence level is 95%. Determine 95% confidence interval for the true mean. The true mean, it means population mean. Mu. Resistance of the population. So now the information that we have in this example, we select a random sample of size 11 from a normal population, so normality is assumed to be satisfied. This sample gives mean resistance of 2.2, and we know that the standard deviation of the population is given by 0.35, and the question is determine 95% confidence interval for the true mean resistance of the population. So this is the information we have. Now straightforward calculations will give this result. X bar plus or minus the alpha over 2 sigma over root n. X bar 2.2 plus or minus 1.96 times sigma, which is 0.35 divided by root 11. This will give 2.2 plus or minus this amount. And as mentioned before, this amount is the margin term. So just subtract this value from 2.2, you will get 1.9932, and add this value to 2.2, you will get this result. So mu greater than or equal 1.99 all the way up to 2.4068. So that's the calculations we have. So mu is between
95%.
Now let's see our interpretation for this result. So again, straightforward calculations will give this result. Now the interpretation, you should write the following. We are 95% confident that the true mean resistance is between these two values. Just saying, we are 95 sure that the true mean resistance is between these two values. Although the true mean may or may not be in this interval, but we are 95% of the intervals formed in this manner will contain the true mean. So again, you don't know exactly if the true mean lies in the interval, but you could say that 95% of the intervals formed in this way will contain the true mean. So that's all for confidence estimation for the population mean mu. Any question? Later, next time, inshallah, we'll talk about the confidence interval when sigma is unknown. I mean, do you ever truly know sigma? May not. In virtually all real world business situations, sigma is not known. If there is a situation where sigma is known, then mu is also known. Because since to calculate mu, you need to know mu. In order to calculate sigma, you should know the value of mean mu. Finally, if you truly know mu, if you know the value of mean, there would be no need to gather a sample to estimate. So if the value of the mean is given, you have to stop because you don't need to select a random sample in order to estimate the population mean. And again, in real life, sigma is unknown. So next time, we'll talk about confidence interval for mu when sigma is unknown. So that's all for today.